Hello everyone, my name is Mason Dumaine, and this is my partner, Adam Warner. We are Team Supfina, and our project is the creation of a full production superfinishing machine. The immediate question that you may ask is, what is superfinishing? Well, it is a method of improving surface geometry using abrasive media. Pictured in the center of this slide is an example of the type of abrasive we will be using in our machine. This cup wheel grinding head is spun against the workpiece at high RPMs. Finishing workpieces in this manner reduces friction between parts, improves surface durability, and can create tight seals between parts. Because our machine is not yet completed and it is infeasible for us to bring in a large industrial machine for a live demonstration, I have prepared a 3D rendered animation to demonstrate the basics of the superfinishing process. First, the workpiece is loaded into the machine and secured into the chuck. Then, the cup wheel grinding head seeks to make contact with the workpiece. Once contact has been made, the surface finishing process begins and the surface is ground. Then, the cup wheel retracts from the workpiece and the workpiece is unloaded and recovered from the machine. Next, my partner Adam will discuss the motivations behind our project.
Thank you. So, pictured here is Supfina's latest machine, the Nano. This machine has perfected the flat finishing process, able to complete each workpiece in under 30 seconds. This, through testing and contract work, has revealed a demand for a superfinishing machine of this speed and accuracy with the ability to work on larger workpieces for the use in manufacturing. This is where we come in. Pictured here is a model representation of the SM814. This machine will achieve the same surface quality as the Nano with a roughness average on the workpiece of less than 0.05 micrometers. A roughness average shown by this graphic is the average distance between the maximum peak and the lowest valley on the surface of the material. Our machine will double the workpiece diameter than the Nano at 270 millimeters. We will do this by applying modern automation techniques such as the Allen Bradley pipeline, which is a collection of hardware and software designed to simplify the automation process, and the use of ladder logic, which is a graphical programming language designed to integrate nicely with the Allen Bradley pipeline. Our best anticipated outcome is to work closely with the mechanical engineers over at Supfina to select all electrical hardware and design an electrical system to best suit their specifications. We are also to create the machine controlling program using the ladder logic I mentioned earlier, and to design the machine interface in which the operator will communicate with the machine. So far, Mason and I have made significant progress, first of which being the selection of all the hardware that goes in the machine. The transformers and power supply were fairly easy to select since it's a similar system as the Nano, so we just were able to mimic that. Safety components, such as this relay pictured here, and the programmable logic controller, known as a PLC, pictured here, were a little more challenging since each one of these individual sections serves a specific function that we had to select. Most difficult was the servo motor drives. There are 3 motor drives that we needed to select for this project. This required power data calculations of the motors themselves, as well as extensive research into the motor drives to make sure that they would serve those purposes. We are proud to say that all hardware for this project has been selected and approved for purchase at $8,000 under our given budget. After that comes the design of the hardware. This starts with a power distribution of 480 volts from an input to 3 major circuits. The safety relay logic and input-output logic are controlled by a 24-volt DC power supply. A transformer converts the 480 volts input into 120 volts to control internal components such as an air conditioner to keep the electrical cabinet cool and safely operated. The most difficult part, surprisingly, was the panel layout, which lays out where all of the hardware is going to go within the electrical cabinet. This was difficult because everything needed to be within a section of similar power to ensure safety of the operator. Next, my partner Mason will talk about his accomplishments in the software.
As Team Supfina's computer engineer, it was my job to define the machine's behavior through ladder logic. The machine operation begins with the loading sequence in which the proper insertion of the part is ensured through a variety of safety checks. Next, the more complex auto sequence defines the surface finishing process. This is fully automated using user-supplied job parameters. Next, the machine is returned to its home state in which all of the machine components have their values checked and reset to their default. Finally, the workpiece is unloaded and recovered from the machine in the unload sequence. The remaining tasks for our project are to finish the remaining PLC program subroutines, including all of the motion control sequences and the fault and recovery subroutine. The next task is to debug the machine, including testing all of the functionality of every part. Lastly, we will need to design an intuitive human-machine interface with keen consideration on what data needs to be displayed. Team Supfina would like to thank everyone involved in the success of our project.